Let us first finish up the polymers revision, and then if you today I'll also do some problem solving in the class once I'm done with the session. Let's see. First, when it comes to polymers, you need to divide these into two types: homopolymers, homopolymers, and copolymers. Homopolymers means only one type of monomer is present. One type of monomer is present. Okay, and if I take glucose as a monomer, right? Then starch, cellulose, okay, dextrin, inulin, right? These are various types of polymers associated with it. Similarly, if I take fructose as the monomer, then sorry, inulin is for fructose. Inulin is the polymer of fructose. Glycogen is for glucose. These are the monomers and respective polymers for the same. Okay. Same if I take ethene, then polyethene. Polyethene is the polymer. Okay. Similarly, if I take styrene, polystyrene, styrene is the polymer. Okay. Like this, if you know the monomer, respective monomer, these are all their polymers which are formed. Okay. Next, if you think about copolymer, copolymer, which means we have more than one type of monomer. If you have more than one type of monomer, then they are copolymers. For example, if I take, you know, SAN, SAN, which is styrene and acrylonitrile, acrylonitrile. Similarly, if I take ABS, that is acrylonitrile, acrylo, acrylonitrile, butadiene, and styrene. These are all various combinations. Okay. Take Buna S. Buna S is for styrene and butadiene. The combination of these two. Next, Buna N. This is for acrylonitrile, acrylonitrile and butadiene. Okay. Nylon 6. No, sorry, nylon 66. Nylon 66 is for hexamethyl diamine plus adipic acid. Okay. Lastly, pteryline. Pteryline. Pteryline, terphalic acid, terphalic acid, and glycol. So combination of these two will give you these various copolymers. Okay. I'm writing the most important ones. There are other copolymers also. Okay. But these are the ones you need to practice. Okay. Which are the homopolymers and which are the respective copolymers. Correct. Now these copolymers can be categorized into many types. Okay. First one, random copolymer. Random copolymer. Random copolymer means if you have n moles of A, n moles of B, and that is forming something as AA, B, A, then maybe A, then B, B, A, B, A, B, like this. So there is no regular pattern. If you have seen, there is no regular pattern when it is random copolymer. Then alternating copolymer, alternating copolymer. Okay, so if I take n moles of A and n moles of B, then it is perfectly sitting in alternate positions. This type of an alternate combination is supposed to be alternating copolymer. Correct. Next we have block copolymer. Block copolymer. Block copolymer is when you have Na plus Nb, okay, giving a particular block of all compounds to start with, like this A, and then we have a range of B, and then A will start. So large portion is covered by only one type of polymer. Next we have graft graft copolymer. Graft copolymer is when you take Na plus Nb, right? Here we have one type of polymer like A, and here like this, and there is one more segment which is made towards B, like this. Okay, so if you have anything of this type of segment, these are called graft copolymers. Clear, everybody? This is the first distinction of the copolymers. Okay, they're categorized into these four kinds. Next, if you notice the classification of polymers, first one is natural polymers. Natural polymers. These are polymers which are naturally observed, okay, which either obtained from plants or animals. Uh, See, anything which is proteins, carbohydrates, silk, clear, uh, natural rubber, natural rubber. Another form of natural rubber is gutta porcha, clear. These are all obtained as natural copolymers. Sorry, natural polymers. Okay. Next, semi-synthetic, semi-synthetic polymers. Semi-synthetic polymers are natural polymers, okay, but we are changing their way of getting polymerized. So the monomer is natural. Monomer is natural source, but modified modified polymers. So we are just modifying them type of polymers. Got it? And typically, cellulose is the best example. Cellulose is being converted into cellulose acetate, cellulose nitrate, right? And rayon, cellulose rayon or cellulose xanthate.
Come on.
What beta? Any doubt? So here you can see cellulose is a natural polymer, but these are all their modified forms. Next. Third one is synthetic polymers. These are completely made by man-made. So examples are these are all man-made and examples being C, polyethylene, polystyrene, nylon 6, nylon 66, synthetic rubbers, and so on. Okay. These are classification of polymers based upon, right? What is the source? This is based on the source. Next, classification based on shape. First one is linear polymers. Linear polymers mainly will have well packed chain like this. So they'll always have this linear form here. Okay. So this will be right. Uh, See, if you have this kind, that means the closeness between the particles will be very high. Got it? And especially like nylons, which will have very high tensile power. So this will have density, high density, high tensile strength, high tensile strength. Clear? High melting point and boiling point. Got it? Right. So these type of examples where you will see, you know, high tensile strength is observed. These are all the ones. Examples, if you notice, silk, cellulose, nylon, any form of nylon, nylon 6 and nylon 66, terriline, clear, and that's it. These are all the ones which you'll see are linear polymers. Next, branched chain polymers. Branched chain polymers. That means we'll have like this, but somewhere we will also have branches in between, like this. Got it? Due to branches, all these properties will become low. Okay, so the same thing, what I have written, now they will all become low. Okay, so you will have low density, low tensile strength. Okay, because of the branching. HDPE, high density polyethylene, and examples LDPE, low density polyethylene. This is the difference between these two. High density polyethylene is maximum going to be linear form, while low density will have some amount of branches. Okay. Other than that, we have glycogen. Okay. Amylopectin. Starch has two parts, amylose and amylopectin. Amylopectin is more of a branch chain form, and amylose amylose is more of a linear polymer form. Got it? Next, third one is cross-linked cross-linked polymer. Cross-linked polymer, as in we will have polymers like this, but suddenly somewhere there is a cross linkage which has been formed here, like this. This kind of cross linkage has been observed. We call it as cross-linked polymers. Now, because of these linkages, now they'll be hard, they'll become brittle, okay? They'll have more rigidity will be high, okay? Typically, examples are all resins. Resins usually have uh, cross links. Few resins include urea formaldehyde, okay, melamine, melamine resin here, phenol formaldehyde. These are the type of examples. Bakelite, okay, Novolac, sorry, not Novolac, Bakelite. So these are the ones which you will see. These are all cross-linked polymers. Okay. Now, this is the next classification. After this, the classification is based on classification on mechanism. So first one we will see is condensation polymerization. Condensation polymerization, right? Which is also known as step growth polymerization. Step growth polymerization. Okay. So basically here we will condense some molecule, right? Is there any difference between hardness and tensile strength? Yes, beta. Hardness is to do with, how much, what do you say, how much amount of strength a molecule will possess, correct? When it is been compressed, how hard it could stay. That is measured on a more scale. If you remember, diamond is very hard, we say, correct? But diamond is not tensile. Tensile means if you twist the molecule, how strongly it can hold, or if you stretch the molecule, how strongly it can hold. Okay, right. Notice this step growth polymerization. In step growth polymerization, we require at least two or more than two monomers. Okay, two or more than two monomers. For example, if I take something like an aniline, so NH2, CH2, N times, and then we have NH2 like this. And I'm reacting this with, acid HCOO, and which is again some, this is X and Y image, this is X and this is Y amount of COOH, right? These two will undergo condensation, right? That means they will remove out the water out of it, and they will combine in this way. NH on this side, and then we will have CH2X, then again NH, Between these two, now there is a bond formation between these two. So NH, double bond O, CH2, Y times, then C double bond O, and we close it here. So like this, if I take n types of moles, okay. Now here the catch is, if you make a polymer of n size, then n minus 1 times of H2O will be released out. Okay, the released out molecule will always be n minus 1 times. Correct. This is how we do the polymerization. Now I can do the same thing, right? Again, using acid and alcohol instead of NH2 and NH2, correct? Now I can take it as OH and OH here. Okay. So here I just need to replace that with OH. That's it. So here we'll have O connection, and here we'll have O connection here like this. Got it? So what do we get? This is like the esters forming. So these are polyesters, and above one are polyamides. These are polyamides, and this is an example of polyester. Mainly the questions revolve around how the monomers are being attached to each other, and how the abbreviative form of polymer is written. This is how we have to write it down. So that is more important. So learn to write how the polymer looks like. Okay, right. Next is addition polymer. Second one is addition polymer. Okay, addition polymer is when you have same molecule, only one monomer is present, that is just converting into a polymer. Okay. For example, if you have butadiene, right? Suppose if you have a butadiene here, 1 and 3 butadiene. If I take n moles of this, Just a minute, guys. Sorry, lost the connection. Right, sorry. Check it out. So check it out on addition polymers. If I take n moles of it, if you get this kind of an addition here, right, then we call it as addition polymers. Okay. So isoprene is one of the most used for addition examples for addition polymers. So if I take n moles of this, right? So this is isoprene, which is the monomer of natural rubber. Now there are two ways it can make into polymer form like this. This is one way, and in this I'm taking a cis form now. Okay, cis polymer. The cis type of polymer is actually natural rubber, and I can take a transform also. That is, if I take the same isoprene, if I do a transform of it like this, okay, and if it is polymerizing on this end like this, and n moles of it, then this is transpolymer. So the transpolymer in this case would be, sorry, I've written it wrong, like this. So if I take the transform of it, this is gutta pocha. Here, this is the type of addition which you will observe. Okay. Now, addition polymer is of many types. One is radical radical polymerization. One is radical polymerization. For radical polymerization, we require radical initiators. That means these are the ones which will help in starting the radical forms, which includes peroxide, okay, any kind of peroxides here, or sulfoperoxides like this. If you have any kind of sulfoperoxides, we can have um, azoperoxides, azo groups like this. Any kind of azo groups we have, these all will help in formation of initiators. So they will initiate to form the radicals, and from there they will polymerize they will start propagating the radicals towards monomers. Okay, right? Most addition polymers are observed in styrene, vinyl chloride, vinyl acetate, methyl methacrylate. These are all various forms. As in, when we go into the reactions, we will see them. Okay. Typical mechanism is the same which we learned. Initiator will first form a radical, and then something of this sort, which is present with our uh, monomer. This is a monomer of some group G. So initiator would come and get attached to it. So we'll get initiator connecting to CH, G, CH with G and CH2 dot. Okay. And this dot will only keep propagating. That's it. So that means it will take the this dot, I would again connect with CH double bond CH2 G. So this radical will again connect here, generating a new radical. Thereby we'll have initiator with CHG, CH2, again CHG, CH2 dot. So this is how it will keep on happening. Okay. At the end, we will do a termination of molecules, right? Done. This is how the polymerization happens. Later on, it will get terminated, so we don't have to worry about how the termination happens. Okay. Usually, what we do here is for termination, we can either use some chain terminators, right? For example, like CCl4, CCl4, which will come out as Cl dot and CCl3 dot. So this CCl3 dot can be used for termination. So if I take this molecule, let's say this way, okay, so it will come and terminate on this end after all the n number of molecules here. So we will have something like CHG, H2, CHG, and this CH2 after n number of times, after n number of times here. So then we will see CCl3 getting terminated at the end. Okay. Correct. These type of terminators are also called as inhibitors. Inhibitors. Other examples of inhibitors being phenols, quinones, right, and amines, various amines. These are all going to act like inhibitors. Clear on that? Right. Next, this is about a radical polymerization. Right. Next, let us see cationic polymerization. Cationic polymerization. So in cationic polymerization, initiators must be something which will generate the cation. Okay, initiators must be something as if they have an empty orbital like this, BF3, AlCl3. So these are all Lewis acids. So we require initiators to be something like a Lewis acid. Okay, or even H plus. These are all going to be Lewis acids. Okay. For example, if you have CH2 double bond CH and G we have, okay, and let's say I initiated this with BF3. So BF3 minus with CH2 and CH plus with G. This kind of a addition will happen. And once this addition will take place, it will start getting polymerized to the next molecule. CH2 double bond CHG. So now this pi bond will attack here. Now that will form BF3 minus with CH2 with CHG with CH2 with CH2G plus, and you can see the progress. Okay. From here onwards, it will start polymerizing. Okay. Clear? So we will take any anion to terminate this. So if you take this, and for termination, If you take n number of polymers like this, let's say we have this n number of polymers forming, that plus some A minus we will take, so that will give us CH2, CHG, and here, and this side we will have BF3, and here we'll have some terminator A. Okay, so that's how we will terminate the molecule. Got it? Now, in which cases we will usually observe this? See, in all the cases, in all the polymers where we will have stable carbocation, okay, cationic addition takes place in stable carbocation cases. Stable carbocation cases. Stable carbocation as in where you have 3-degree carbocation, benzyl carbocation, correct? In such cases, you will see uh, carbocation polymerization is most favorable. Okay. For example, if I take isobutylene, if you add it with H plus, now you will notice that H will get added here, positive charge will come here. So this is a very stable carbocation. So then this stable carbocation will be acting again on this pi. So pi will get added here. So this way again I'll get positive charge here. Okay. So this type of attachment of positive charge is observed. Sorry, CH2 will be there. Like this, positive charge will be here. Okay. So on this positive charge, again you will see the addition happening here. Correct. So that will keep on proceeding for this type of polymer where you will have, if I write directly the polymer form here, how does it appear? It is like this, right? This is the way it will appear, and this will continue on this side and this side. Okay. In a short form, how do I write that? I need to show that these two, this side and this side, it is polymerizing. Okay. So I will write it this way: carbon with CH3 and CH3 here, and this side, uh, one carbon we have CH2 here, like this, and this side it is getting polymerized to N types. This is the way we will write down, and this is butyl rubber. This is butyl rubber. Please check if anybody has a doubt on cationic polymerization.
So can you please explain the last one?
What, Akhil?
So, so writing the condensed form of the
I can't hear you
polymerization.
properly.
So can you please explain the last part one more time?
Which will act?
So can you please explain the last part one more time?
Ciao. See, how you write down the polymer is this way. First, you got a carbocation here, right? This one with uh, positive charge here, isn't it? And this side, the growth is happening, correct? So CH3 will keep stretching on this end, and this end also it will start stretching. So these two will not be stretched, right? The stretching is happening on this end and this end. That's why I have written that line. This end it is stretching, and this end it is stretching. Clear? and that too n times it will keep polymerizing on this end and this end. Okay. Right. Now check out the anionic polymerization. So if it is anionic polymerization, right, we require anionic initiators. So initiators are supposed to be strong bases, right? RLI, okay, RLI, PHLI, right? NaNH2, right? And NH minus Na plus. These kind of very, very strong bases can be used for initiating a reaction. Okay. Let us take with an example. Here, uh, monomers which can form monomers which form stable carbanion. Stable carbanion is supposed to be checked. So which are stable carbanion here? CH2 double bond CHCl, CH2 double bond CHCl, CH2 double bond CHC, CH3 with C double bond OCH3. Okay. C6H5 CH double bond CH2. Okay. Right. So this is vinyl chloride. This is vinyl cyanide or nitrile, vinyl nitrile or acrylonitrile, and this is methyl methacrylate, and this is styrene. So notice styrene has an advantage that it can go for carbocation and mechanism also, radical mechanism also. It can go for anionic mechanism also. In all the cases, it will show the polymerization pretty easily. Okay. Next. See, in all of this polymerization, whether it is cationic, anionic, acha, I didn't say the mechanism. Let me show. So CH2 double bond CH, let's say some group is here. So initiator like NH2 minus will start initiating, pushing a bond here and getting a negative charge on this. So you will see that CH2, NH2 would happen here, and then CH and G would form here. Correct? And if it polymerizes to N, after N steps, what you notice is that we will have same group here, that is CH2, right? CH2, and then we have CHG here, CHG, and this is getting polymerized. On this side, we have NH2, and N number of times it get polymerized, and we will have um, sorry, write it as a separate molecule here. This side I'll write CH2 and CH2 and NH2 here, and this side some CH2 and G of N times, right, with minus N. Okay. This is how after N steps. Okay. So let me put it as N plus 1 here, N plus 1 step. So therefore, n number of moles will be formed here, and this is how the polymer would be observed. And this side again, we will terminate it with some acid like H plus or something, and we will close it up. Yeah. See, for initiating these addition reactions, right, one of the important catalysts that is used is, Ziegler-Natta catalyst. Okay, Ziegler-Natta catalyst. This will mainly help for, all the chain growth polymerizations. Ziegler-Natta is basically C2H5 ethyl, you know, thrice aluminium plus TiCl4. The combination of these two polymers, right? This would give mostly, linear polymerization. It will avoid any kind of branching. So that will give you more harder or high tensile, high density kind of polymers. Okay. HDPE is made using Ziegler-Natta catalyst. Okay, as an example, you can remember that. Next, this thing is classification based on intermolecular forces. I'll keep it in short here. See, so first one are elastomers. First ones are elastomers. Okay, elastomers, right? This will have a random polymerized form. So random polymerization happens here, correct? This must have definitely some crosslinks. Crosslinks must be present, okay? And weak van der Waal forces, between chains, polymer chains. Then we will see these are elastomers, okay? Correct. Best examples, vulcanized rubbers. So vulcanized rubber is natural rubber. If we add some amount of sulfur connections will come between the two polymers, between the two polymer chains. So that is called vulcanized rubber. So elastomers are one of them. Okay. Second one, fibers. Okay. Right. In fibers, two chains, two chains held by intermolecular hydrogen bonding. Interhydrogen bonding. So if interhydrogen bonding are there or high dipole moment, high dipole attraction. So if you see high dipole attraction or strong interhydrogen bonding, that means these are of fiber forms. Okay, this makes it high tensile strength. High tensile strength. Okay, and high melting point and boiling point and low solubility. Low solubility. Okay, examples nylon, cellulose, wool, silk, terylene, and so on. These are the examples. Next one, thermoplastics. Thermoplastics. Okay, this will have both ordered, and random polymerization. Some part it will be ordered, some part it will be randomly aligned in the entire region. Okay. Correct? These have intermolecular forces, intermolecular forces between elastomers and fibers. So these are somewhere between those two. It's not completely hydrogen bonded or dipole-dipole bonded, or not simply van der Waal interactions. So it will have more than van der Waal, but less than hydrogen bonding or less than uh, strong dipole-dipole attractions. Okay. Okay. They're generally hard at room temperature, and soft at high temperature. Soft at high temperature. Okay. So it can be reformed into original solid state by cooling and molding. So you can mold this polymer and convert back to the original one if it was at higher temperature. Okay. So usually all the plastics which we use, those are all generally thermoplastics. Okay. So most ethylene derivatives like PVC, okay, and PAN, polyacrylonitrile, and polythene, and these are all, forms of thermoplastics. Of course, these thermosettings, okay, this will become hard on, heating. It will become hard and heating and stays permanently in a solid residue. So it will exhibit into a new solid residue which cannot be remelted or molded back to the original shape. Okay, must have cross links. So this must have cross links here. Okay, uh, and these are generally brittle. These are brittle as well as I think this will have low low density as well. Okay. Now, see examples being all resins. Resins are the best example. Bakelite, melamine, and then urea formaldehyde, phenol formaldehyde, and so on. These are all going to be thermosettings. Okay. While thermoplastics generally all are linear, okay, linear polymers, right? So these are the main differences, guys. Check it out. Elastomers, fibers, thermoplastics, and thermosettings. Done? Done. Now see, as reactions, what could be asked? Polymer reactions. First is about natural rubber. So we'll discuss all the rubbers. See, if I take 2 moles of ethene and then you treat it in the presence of Cu2Cl2 in neutral medium, ammonium chloride, then this will undergo addition reaction. I mean, the coupling would happen here. So C triple bond CH. Okay. And this on further addition of HCl will become CH2 double bond CH, CCl double bond CH2. So this is called fluoroprene. This is called fluoroprene. Fluoroprene, if you use Ziegler-Natta catalyst of n moles, it can polymerize into either what do you say, trans form or a cis form. So the trans form of it, that is C double bond C, methyl here and methyl here, leaving behind chlorine and another methyl here like this, going n number of times like this. Right? This is the trans form of it or a trans polymer, and which is called as neoprene, which is synthetic rubber. Very important reaction. Remember, in rubbers, the uh, artificial rubber or synthetic rubber, how it can be made. This is how we can see it. Okay. So next, check out Buna N. Um, First we'll see Buna S. Styrene, Buna S. So if I take n moles of butadiene, CH, CH double bond CH2. So this is 1,3 butadiene plus n moles of styrene. In that case, we have to become CH2, CH double bond CH, and from this CH2, it will be connected directly to CH with styrene and another CH2. So if this goes n number of times, then this is Buna S. Please remember this structure. Okay, you need to identify, given the options, you should identify what is the right polymer. Okay, what are their monomers. Next, Buna N. Okay. Buna N would have similar thing, n moles of this plus n moles of CH2 double bond CHCN, acrylonitrile. So if it meets acrylonitrile, same logic, CH2, CH double bond CH, CH2, CHCN, and CH2 n number of times. So this is Buna N. Okay. All right. Next, another one is thiocol. Okay. Thiocol is made up of this one, 2 moles of ethylene dichloride. This is ethylene dichloride. Okay, plus N, S, S, and A. Okay, basically sulfide, Na2S2 sulfide. So this will combine with each other, CH2, CH2, and if I cross this here, S and S will get combined with another CH2, CH2 like this. Okay. So all these sulfur chlorine groups are replaced by sulfur here, sulfur and sulfur bond here, and you take it n number of times. This is called thiocol rubber. Okay. It is mainly used in making that, tank lines, engine gaskets, rocket fuels, right? So all of that. Next, we'll see nylon 66. Nylon 66. Nylon 66 is if you take adipic acid, HCOOH, four times COOH. This is adipic acid, and treat that with NH2, CH2 six times NH2. This is hexamethylene diene. It is also of N moles we'll use. So at around 280 degrees centigrade and high pressure, you'll see the product form. Product is, O, C double bond O, right? And then we have CH2 four times, and here we'll have connection of C double bond O NH, and the other side we have CH2 six times with NH getting combined. Yeah. Please, again, I'm telling you, this is the part which you need to write and learn how the exact polymer looks like. So this is nylon 66. This is the most important part, guys. Learn to write how the polymer looks like. Okay. This is nylon 66. Similarly, I can have nylon 610. Nylon 610 is same hexamethylene. Everything is same except the acid is different. Except the acid is different. So let me just copy that here. Everything is same except here we will have 10 carbons in an acid here. So we'll have to have 10 carbons. So that means this should be 8. So here it is 8. That's it. So, and if you have total of 10 carbon acid, this is called sebacic acid. This is sebacic acid. So that will give you nylon 610. Okay, right. Next, nylon 6. Only if you have nylon 6. Right. See, nylon 6 can be first made it by this case 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Got it? So you can see if we have bromine here and bromine here, and you react this with magnesium and dry ether of one equivalent. So one side we will get MgBr here, and the other side we have Br. So this minus will go and attack here, remove this Br. So we'll get minus MgBr2. This will convert into a cyclohexane. The cyclohexane part, when you react with Cl2, NBS of one equivalent, you will get bromo, this, and with aqueous KOH, we will get alcohol. Okay. So what we got here is cyclohexanol. That when you treat with PCC, we'll get this as ketone. And this ketone, when you treat with NH2OH, will form double bond NOH. This is oxime. Oxime, when you treat it with H plus and heat, right? So it will undergo cyclization, Beckmann's rearrangement. One second. Sorry. Check this out. So we will get a Beckmann's rearrangement like this with one nitrogen place here, double bond, okay, NH. So this is called caprolactam, which is like the monomer. Caprolactam is the monomer. And we take this caprolactam, take it to the high temperature, 260 to 270 degrees centigrade with H2O. It will start polymerizing. Now, how do we write polymerized form? Acid on one end, then we have CH2 five times, and then NH on the other hand. So that is how it will get polymerized to form N times, which is nylon 6. The entire reaction sequence is always asked in exam, so please learn properly how we can go up to caprolactam form. Finished, everybody? Right. Next polymer you need to learn is melamine formaldehyde. Formaldehyde resin. See, melamine is this structure where you will have we have nitrogen connected this way, double bond, and double bond here with NH2, NH2, and NH2 this way. Okay. If I take formaldehyde to act here, correct? So then we will get an intermediate where this end we will have NHCH2OH. And if this gets polymerized, okay, on this end and this end, the polymerization would happen here. So what do I get? We will be writing this as N on this end and CH2, right? And this side. That OH will go and this will go and N times it will happen. And this is going to be melamine formaldehyde resin, MFR. Clear on this? Next one is bakelite. bakelite. Okay. See, first, if I take phenol and add it with formaldehyde in H plus, then it will give two products. One is at ortho, the other one is at para, OH, OH here. Okay. Now, if the ortho form undergoes polymerization, so if I take n moles of this, and if this gets polymerized here directly, so how does it look like? So we will have this way with H here, you have OH, and this side it is getting connected, and this side also it will get connected like this. So what do we get? Like this, we have n number of n length followed, so which we call it as novolac. Novolac is a linear polymer. Linear polymer. Okay. Now, if you take some molecules of this n moles of ortho and some n moles of para, some n moles of para in this case, and then polymerize it. Okay. So in that case, we will have this end getting polymerized, OH, and this end it will attach to the next molecule. This is a Novolac form. So you can see this is like a Novolac form here. Okay. And at this point, you will see CH2 connecting to the other position here, OH. That means this is from the para end, and this ortho end is carried. So like this, we have CH2 getting connected to this one. And this side also it will keep growing n number of times. Okay. So this will keep growing n number of times. So this kind of a structure is called bakelite. So you can see bakelite has complete cross-link polymers. Okay. Next one is dacron. Dacron is when you have ethylene glycol of n moles and treat that with phthalic acid. So terphthalic acid. Okay. This one is terphthalic acid, and if you heat it, it will start forming O, CH2, CH2, and it is connected by C double bond O. Okay. Sorry, O C double O, C double bond O, like this with C double bond this way n number of times, which is dacron. This is dacron. Yeah. Next one, biodegradable polymers. Only two important polymers when it comes to biodegradable polymers, right? One is PHBV. PHBV. PHBV is poly, right? Hydroxo or hydroxy butyrate, polyhydroxybutyrate, and you know beta beta hydroxy valerate, butyrate and valerate. Butyrate is 4 carbon acid, valerate is 5 carbon acid. Okay, right? So one should be uh, hydroxy valerate, and another one should be hydroxy butyrate, C. So basically, if you take four carbon acids, COOH, alpha, beta, at beta position we have OH here, and that you treat with COOH. Again, we have OH here. So this is beta. So 1, 2, 3, 4, 5. 1, 2, 3, 4. So this is hydroxy butyrate, and this is beta hydroxy valerate. Both at third position here. And if these two will undergo polymerization here, how will that be? See, from this oxygen end, we need to start polymerizing. So we will have oxygen here, and then connected to a carbon which already has one carbon on it. So let me put it this way, like this. There is a methyl here, and we can see this carbon now, this carbon, and then we have C double bond O connected to this oxygen, right? And next carbon has one more methyl, which is connected to two more carbons. Then we have C double bond O. This connection ends here like this. Okay. And if this goes n times, then that is PHBB. Here. Second one is poly glycolic acid and polylactic acid. Don't worry about the structure wise. Just remember these are two examples, which we'll be using for using as biodegradable polymers. Okay. Next, if you notice molecular mass of polymers, right? Normally, molecular mass is expressed in two different ways when it comes to polymers. Second O is connected to an ethyl group. Yeah, correct. Sorry. This is one extra carbon. Sorry. Thank you. C double bond O this way and that. Right. Right. Check out. Molecular mass. One is number average molecular mass. Number average molecular mass, which is represented as Mn, which is sum of Ni into Mi whole divided by sum of Ni. Okay, clear? So basically, how many number of polymers we have and what is their respective mass, right? So that multiplied by the total numbers divided by the total numbers, right? So that will give you uh, number average molecular mass of a polymer. Okay, right. Next, second one being weighted average, weight average molecular mass, which you write it as MW. Okay, so MW will be sum of Ni Mi square divided by summation of Ni Mi. Ni Mi. So this is called number, weighted average molecular mass. Okay, right. Next, the ratio of these two is called as PDI, which is poly dispersity index. Polydispersity index, PDI. So PDI is equal to weighted average molar mass by number average molar mass. Okay, right. So PDI gives us an idea about how natural or how synthetic the polymer is. Ashwant, which one better? Weighted or PDI?
Sir, both.
See, if you have n number of polymers of different molar mass, right? I meant to say something like if you have nylon 66, for example. Okay, so if you take nylon 66, like how many number of adipic acids we have, how many number of what do you say, hexamethylene groups we have. Okay, let's say you have taken some 2000 and 2000 of both of them, correct? So what do you do? That is 2000 number here. That 2000 into molar mass of one plus another 2000 into molar mass of the other, that divided by total number of particles, which is 2000 4000, correct? So that you divide it. Understood? Clear? So how many total number of monomers we have? Whatever the mass you will get, that is the average molar mass based on numbers. Okay. Second is, if you have to find out the weighted average, this time same thing you do, but this time you square the molar mass again divided by the molar mass here. You know that in statistics these two kind of averages are always used. If you have to find out an average, this is like the root mean square kind of root mean average. This is a simple mean average. That's one clear beta.
Yes.
And the ratio of these two is what we call it as the PDI. Okay, polydispersity index. Now polydispersity index is mainly used for identification of natural and synthetic polymers. So pdi value is close to 1, then most likely most likely it is natural polymer. If pdi is you know greater than 1, right, then most likely it is synthetic polymer. Is synthetic polymer. Okay, that's the idea we need to have from molar mass here, right? So given any particles, you just need to figure out how is the molar mass, and based on that try to get to the idea of what is the pdi value, right? So questions will be asked, I mean, last time when you had wt also, if you recall, you have been asked few questions on number average and weighted average and finding out pda. Okay. So please go through them once again. So I hope you should be able to figure it out. Okay. I gave you last time, if you recall, I gave you the notes. If needed, I'll send it again. But I gave you the complete list of polymers, okay, and how to write the repeated units. Got it? Polymers and the repeated units. Learn to write those polymers as well as the repeated units. Okay. I'll do one thing. I'll just mark which are the most important ones which you need to learn from the syllabus point of view. Just at least learn to write those, repeated units, how it looks like, and what is that polymer. Okay, what is the name of that polymer? So just please go ahead and check. Okay, everybody clear on that?
Yes, sir.
Right. Okay. So we'll stop it here now. So we'll finish this off. I hope you can complete the theory part today. Okay. Uh, One thing I have pending is about the basicity of amines. Okay, I'll give you a list of compounds today. First, figure out all the cases. I'll be making a discussion maybe today or tomorrow, but make sure that you go through those questions of all the basic characters. Okay,
Okay,
right.
sir.
So, see you in the class.